Yeah, an empirical formula, it's just a chemical formula, but by definition, it's the smallest whole number ratio. So sometimes you'll divide by 2 or divide by whatever common factor those subscripts have. Writing that, I'm going to come around with calculators if you don't have one yet. Go ahead and grab one. Tomorrow, if you bring something different for a backpack, then don't bring your own calculator if you usually bring your own. Spencer. Anyone else need a calculator? Here. Got 2 more up here. Hallie, do you have your own?
Yeah.
Okay, so when you have a molecular formula, it's really easy to figure out the empirical formula. If you can just see they're both numbers are even, or they're both divisible by 10 or something like that, you just reduce it. So the next thing I want us to go to is, let me go back to one that matches yours. There we go. Let's just decide whether these are empirical or molecular. So the first one says N2O4. Is that the simplest ratio, or could that be reduced? Reduced. It could be reduced. Therefore, we know we're looking at a molecular formula. So I'm just going to put an M maybe on top of that one or next to it to remind myself. That's a molecular formula. What about NO2? That's an empirical formula. Now, there's a possibility it could also be a certain compound's molecular formula, but it's definitely an empirical formula. What about with 3 elements, CH2O? I'm going to go with empirical. And C11H22O11, what's that? The molecular, what are those divisible by? 11, and so that would give us that empirical formula that's on the left. So I just wanted to go over recognizing those before we get into something a little more complicated. So let me pull up the slide that goes along with the next little part here. So I'm just going to pull up your document. Okay, so if we need to come up with an empirical formula based on mass data, this is related to what you did in the lab last week, where you had a mass of zinc and you converted it to moles. You had a mass of chlorine and you converted it to moles. And then you took those moles, and you remember you found the whole number ratio, and you used that whole number ratio to find your chemical formula. So step 1 is going to be to convert grams to moles of each element. Step 2, divide all moles by the smallest number. And then step 3, use those values of subscripts in the chemical formula. Most of the time, you're done by that. Step 4 says if a fraction is present, you might have to multiply by a factor to have whole number ratios. But most of the time, they're going to start off with whole numbers in the first place. So let's do it with this example that you have on your sheet. Find the empirical formula for a compound that contains 42.05 grams of nitrogen. So I'm going to underline that. And 95.95 grams of oxygen. All right, so step 1 is to convert grams to moles. To do that, we're just going to write down our mass, 42.05 grams, nitrogen. because I know it's part of a compound, it's not a diatomic here, it's part of a compound. It's not pure nitrogen. So therefore, its molar mass is just straight from the periodic table. So somebody with some good eyes. Let's see. Hallie, can you see nitrogen's mass on the periodic table over there? 14.0067. All right, thank you. When in doubt, go to the hundredths place. That'll be good enough here. If you wanted to give more, you totally can. But this will be good enough for us. If we stick with 4 sig figs throughout this problem, we'll be in good shape. And Blake, can you do that calculation for me real quick? Okay. Is it exactly 3?
Yeah, pretty much. I mean, you can round each one to 3.001.
On this one, you would be safe to do that. It's true. Just to teach you guys how to do that on some of the future ones, you'll want to keep at least as many sig figs as you start with. But to be honest, you'll get the same answer on this particular one either way because it is so close. But in general, when you're working through these, if you round too much, you do run the risk of getting an incorrect answer. All right, we're going to do the same thing with oxygen. So let's do that. 95.95 grams of oxygen. Mole goes on top, grams goes on the bottom, so it will cancel. Sydney, what's the atomic mass of oxygen?
16.00.
Good job, that's right. It rounds to 16.00. And then I want you guys to do that operation once you get that down and you're ready to. And I'll get somebody to tell me what you get for that. Wilson's got it. What is it, Wilson?
2 oxygen. For that, 6 moles.
Yeah. And tell me, will you round, what, do you still have it in your calculator right now?
It was 5.996.
Okay.
87.
So it even does round to 6 in the end. I'm going to, just to see the example this way, because again, this one rounding does work for you, but on some on your assignment, you do have to make sure that you keep plenty of sig figs, otherwise you can get the wrong answer if you do round to too few. So that is the number of moles that we have in front of us. What you're going to do next on a problem like this is you're going to write down the chemical formula as if those are your subscripts. So I'm going to write down a chemical formula of N 3.001, O 5.996, and that doesn't look like any chemical formula I've ever seen before because it's got all those decimals on there. So what you need to do is you divide by the fewest number of moles. Okay, what number is smaller, 3.01 or 5.996? 3.001, huh? So I'm going to divide both of those by 3.001. Divide by the smaller number. And that is going to give me my final answer here, N1O2. Because your final chemical formula needs to be in simple whole number ratios. And that's the empirical formula for this compound. You cannot use grams as subscripts. Okay, you can only use moles as subscripts. And then you divide by the smallest number in order to get that into a chemical formula with a whole number of subscripts there. Okay, raise your hand if you have any questions about where any of those numbers came from or how I got those number of moles or anything. All right. Well, there's a term for what we just talked about, this whole number ratio, and it's called the law of multiple proportions. So let me just pull that up for you to get that down. This was some evidence when they were first deciding that, hey, everything really is made of atoms. This idea that when these compounds came together, they always came together in simple whole numbers. So they said there must be some kind of simple building block that makes up everything. And the mole concept allows us to see that relationship. So when atoms come together in compounds, they're going to come together in relatively simple whole number ratios. Once you get that down, you can flip the sheet over and we'll do another problem a lot like that last example, only it uses a percentage instead of grams, but it's really easy to deal with that. Anybody need more time here? Flip over back to your sheet. Okay, so on some problems, instead of telling us grams, they give us percentages instead. But it's actually just as easy to deal with these. So if I had a problem like this one and it says this compound, a complex name here, 1,6-diaminohexane, is used to make nylon, what is the empirical formula of this compound if it's 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen? Instead of dealing with all those percentages, if we just change all of those percent signs to grams, we're just assuming that we have 100 grams of the compound, and you can still work through it just like we did the last one. So when you're given percentages, just change percent signs to grams for each element, and then we're going to go from there. We're going to convert our grams to moles and use those moles as our subscripts, dividing by the smallest number to get the simple whole number ratio. So I'm going to say 62.1% carbon, or now grams of carbon. I'm going to convert that to moles. Using the atomic mass straight from the periodic table. I'll do the same thing with the hydrogen there, 13.8 grams of hydrogen. Use its atomic mass from the periodic table. And then same thing with the last one, 24.1 grams of nitrogen. Okay, let's do all that division and get some number of moles. Give me at least 3 sig figs in your number of moles. This kind of stuff, your final answer will be around to the nearest whole numbers, but as you're working through it, you need to keep at least 3 sig figs, otherwise you may not get a good answer. Let's see, Caitlin Vining, did you get your moles of carbon yet?
I got 5.17.
Good answer there. 5.17 moles of carbon. Wilson, did you get moles of hydrogen?
Yes.
What'd you get?
13.704.
Thank you. And you can't have too many decimal points at this particular step, so that's great. And then Eric, are you on nitrogen yet?
Yeah, I got 1.720.
All right. Okay, so I'm going to take those numbers of moles and I'm going to start off by using those as my subscripts. I'll do it over here on the left side. So I'm going to say C 5.17, H 13.7, at least 3 sig figs, and then nitrogen 1.72. Now that doesn't look like a normal chemical formula because those aren't whole numbers. To take them into whole numbers, I need to divide by the smallest number. Okay, which is smallest? 5.17, 13.7, or 1.72? 1.72. So let's divide all of those by 1.72. Okay, so for carbon, I'm getting 3.005. At this point, we're going to round. If it's close to a whole number, if it's pretty close to a whole number, you're safe to round here. So I'm going to go with my final answer is carbon 3, hydrogen, let's check it out, 13.7 over 1.72. 7.96, that's really close to 8, so I can call that 8. And then nitrogen's obviously just going to be 1 because it's divided by itself. That down there, at the very bottom of the screen there, we went all the way down. That turns out to be my final answer. That's the empirical formula for this compound. So there's a lot of steps there, but let's just review. If you have percent signs, just change them to grams. And then you're going to convert to moles. Use those numbers of moles as your subscripts. And then to get it to a whole number, you'll probably need to divide by the smallest number. And that'll give you a simple whole number ratio. All right, so that's how you find an empirical formula for mass data if it's grams, or percent data if it's percentages. The last thing I want to talk about is what if they want you to find a molecular formula that's not necessarily the simplest whole number ratio. To do that, they have to give you one more piece of information, which is a molar mass. So I want to look at this chart that's on your notes page. Before I click, does anybody need more time with these numbers up here? All right, let's look at that chart that you have down below. And it kind of just reminds us of some relationships between the molar mass and these different compounds, whether they're simple whole number, like a empirical formula, the simplest ratio, or if they're a little bit more interesting numbers like some of the others. The first three on there all have the same empirical formula as CH. Now CH molar mass is 13, but if you double the number of atoms and you have C2H2, look what happens to the molar mass. It gets doubled. Well, that makes sense because you double the number of atoms. If you have a compound that's C6H6, now it's 13 times 6, right? It's a factor. So every time you double or triple the formula, there's a factor that you're multiplying times. And the same thing with the next three compounds on there, the three different compounds. We've got a different molecular formula for each of them. They have a basis of 30, and then 2 times 30 or 6 times 30. You multiply times some factor. So I call that the molecular factor, and that's the link between an empirical formula and a molecular formula. Well, let's try this last problem on the page and try to find that factor as a way to try to relate a molecular formula to an empirical formula. This is the last one we'll do together here. This is when you have questions about molecular formulas. It says, calculate the molecular formula of a compound whose molar mass is 60 grams per mole, and the empirical formula is CH4N. First thing you need to do is find the molar mass of the empirical formula. So let's find the molar mass of the empirical formula. Okay, that's CH4N. So that's going to be carbon plus 4 hydrogens plus nitrogen. I'm getting 30.06. to find the thing that I call the molecular factor, you're just going to divide the molecular molar mass which is given to us over the molar mass of the empirical formula. And it's going to be a simple whole number. In this case, it's 60 over 30. So what's my factor here? What's my factor going to be here? What do you think, Turner? If it's 60 over 30? 2. So that means if the factor is 2, it means we need to take that empirical formula and we need to multiply everything in it times 2. So I'm going to just double everything. We'll have C2, H, how many H's? 8. And how many N's? 2. Now this compound would have a molar mass of 60. If you wanted to go back and check, its molar mass is 60. And of course, it still has that same empirical formula if you were to reduce its ratio. So that's how you're going to find the molecular formula when you have an empirical formula. On your assignment that you're about to work on the back of it, you'll have to find the empirical formula with all the steps we went over previously on the last 2 problems, and then they'll give you a molar mass to find the molecular formula as well. It's just based on this ratio. Does anybody think you have any questions at this point? All right. I wanted to kind of